everybody. Welcome to Abu Smart video channel, under which you can obtain many applied mathematics tutorials. For today, we will start applied mathematics 2 that start with a sequence and a series. Under this chapter, we will see what a sequence and a series is, and then we will see applied problem whose solution lead a sequence and a series. So let us start what a sequence and a series is, and let me define a sequence. So sequence can be defined as follows. Sequence is a function whose domain is the set of all non-negative integer greater than or equal to a given integer m, that is usually 0 or 1. That is usually 0 or 1. But a sequence is represented by a subscript notation rather than a standard function notation. So we can say that sequence is represented by subscript notation rather than standard function notation. That is, if A is a sequence, and n is a number in the domain of a sequence, n is a number in its domain, then the value of A at n, at n is represented by an, rather than A at n. In case of a function, if f is a function and n is a number in the domain of f, then the value of f at n is denoted by f of n, but not fn. If the sequence is written as a sequence n start from m to infinity, that is equal to a1, a2, a3, and continue, which is equals to an. Here, the number n is called an index of the sequence. The number m is called initial index. This list of numbers are called terms of the sequence, where an is the entire sequence. So sequence is represented by an when n starts from the initial index to infinity. Next to this, let us see the example of the sequences. Example: list a few terms of the following sequence, a few terms of the following sequences: A, say n over 1 minus 12 when n starts from 1 to infinity. B, 1 over n from 1 to infinity. C, 3 plus minus 1 the power of n from 1 to infinity. D, recursively defined sequence A1 is equal to 2, 5, and an plus 1 is equals to an minus 5. Let us see these sequences. So, if we want to list a few terms of these sequences, when n is equal to 1, the first term of this sequence is equals to 1 over 1 minus 2 times 1. That is equals to 1 over minus 1, which is minus 1. The second term of the sequence is 2 over 1 minus 4, that is 2 over minus 3, which is minus 2 over 3. The third term of the sequence is 3 over 1 minus 3 times 2, that is equal to minus 3 over 5, and continue like this one. And for the sequence 1 over n, when n starts from 1 to infinity, the first term of the sequence is 1 over 1, that is 1. The second term is 1 over 2, and the third term is 1 over 3, and so on. When we come to the third sequences, which is 3 plus minus 1 the power of n, when n starts from 1 to infinity, the first term of this sequence is 3 plus minus 1 the power of 1, that is 3 minus 1, which is 2. The second term is 3 plus minus 1 the power of 2, that is 4. The third term is 3 plus minus 1, which is 2, and the fourth term is 4, and continue. The sequence for the recursively defined sequence A1 is equals to 25. A1 is equal to 25, and an plus 1 is equals to 20 minus 5. Then, since A1 is equal to 25, since A1 is equals to 25, and an plus 1 is equals to an minus an, A2 will be 25 minus 5, that is equal to 20. A3 is equals to A2 minus 5, that is equal to 20 minus 5, which is 50. And the next term is 50 minus 5, that is 10, and continue. So this one is two ways by which we can describe a sequences. That are we can describe the sequences by listing it is few terms, and also we can describe the sequences by a formula. Let us take the other example. Write a general formula for the n star. General formula of nth term for the following sequence. For the following sequences. Let the terms of the sequence be 1/2, 1/4, 1/8, and continue. B 1/2, 2/3, 3/4, and continue. C, let me say 3, 5, 3, 5, 3, 5, and continue. When we see the behavior of this terms, the general formula of these sequences, this list of numbers can be written as or can be represented by 1/2 the power of n when n starts from 1/2 the power of n when n starts from 1 to infinity, when n starts from 1 to infinity, when n starts from 1 to infinity. And the second list of terms, the second sequence can be represented or can be written as n/n plus 1, n/n plus 1, when n starts from 1 to infinity, when n/n plus 1, when n from 1 to infinity. And when we observe these sequences, this one is 4 plus minus 1 the power of n. We can write the sequence as 4 plus minus 1 the power of n when n starts from 1 to infinity, when n starts from 1 to infinity. So this two example shows us the two ways by which we can describe a sequences, that are one is by listing its terms, and the second one is by writing the general formula for the nth term of the sequence, for the nth term of the sequence. Next to this, let us study about the convergence of the sequences. Convergence of the sequence convergence of the sequence. We say that a sequence n starts from 1 to infinity is said to be is convergent sequence if the limit of this sequence exists as a number, That means we say that the sequence n from 1 to infinity, or say n from m to infinity is convergent if the limit of fn, if the limit of an as n goes to infinity exists as a number, That is, the sequence n starts from 1 to infinity is convergent if and only if the limit of an as n goes to infinity is a fixed real number, Otherwise, the sequence is said to be convergent. Otherwise, the sequence is said to be divergent. That means if the sequence fails to be convergent, it is divergent sequence. It is divergent sequence. Okay, the sequence is convergent if and only if the limit of an as n goes to infinity exists and a fixed real number. The existence of the limit is not sufficient. The limit of this sequence has to be exist, and also a number has to be exist and has to be a number for the convergence of the sequences. If we take an example, let us take the example of the sequence. Take the sequence 1 over n and start from say 1 to infinity. Is convergent, since the limit of 1 over n as n goes to infinity is equals to 0. That is a number. If we take the sequence n plus 1 over n when n starts from 1 to infinity, is also convergent, since the limit of n plus 1 over n as n goes to infinity is equals to 1, and that is a fixed real number. Let me take a sequence 5 times n minus 3 over 4 n plus 7 when n start from 1 to infinity. Is convergent. Since its limit, the limit of 5n minus 3 over 4 times n plus 7 as n goes to infinity is equals to 5 over 4. That is a fixed real number. Whereas the following sequences are divergent sequence. Take the sequences 3 plus minus 1 the power of n start from say 1 to infinity. Let's take this sequence. This sequence is divergent sequence, since the limit of 3 plus minus 1 the power of n as n goes to infinity doesn't exist. And take the sequences say n start from 1 to infinity is divergent. Since why the sequence is divergent? Since its limit is infinity. Since the limit of n as n goes to infinity is equal to infinity. That is not a number. So the sequence is said to be divergent sequence if it is limits, the limit of an as n goes to infinity is not a number or doesn't exist. It's not a number or doesn't exists. If this one is about the convergency of the sequences, let us see the classification or types of the sequences. Types of sequence. Types of the sequence. We can classify the sequence in different ways. Among them, we can classify the sequence into increasing sequence and decreasing sequence. Into increasing sequence, monotonic sequence. Let me say monotonic sequence. Monotonic sequence. Monotonic sequence. Let AN be a sequence. Let AN be a sequence. Be a sequence. Then we say that AN is one increasing sequence. If AN is less than AN plus 1 for all n. We say that a sequence AN is increasing sequence if every term of the sequence is less than the subsequent terms, and greater than or equal to the preceding term. If every term of the sequence is greater than the preceding term and less than the subsequent terms. Next, we say that the sequence AN is decreasing sequence if AN plus 1 is less than AN for all n. If AN is greater than AN plus 1 for all n, in the domain of that sequence, and we say that AN is monotonic sequence if it is either increasing or decreasing, So, if AN is a sequence, then we call that sequence is an increasing sequence if AN is less than AN plus 1 for all n. We call that sequence is an a decreasing sequence if AN is greater than AN plus 1 for all n. And the sequence is said to be monotonic sequence if it is either increasing or decreasing. So let us take an example of this sequences. The example for those. Okay, for example, a sequence n when n starts from 1 to infinity is what? Increasing sequence is increasing. So what do you say about the sequence minus n if n starts from 1 to infinity? Is it increasing or decreasing? This one is decreasing. Is decreasing. So they are take a sequence 1 over n when n start from 1 to infinity. This one is also decreasing sequence. So all are monotonic. All are monotonic since they are increasing, since they are monotonic. So one is increasing and those two are decreasing sequence, so they are monotonic. But there are sequences that are neither increasing and decreasing, so they are not monotonic. For an example, if you take the sequence 3 plus minus 1 the power of n when n starts from 1 to infinity, this sequence is not increasing and also not decreasing sequence, so it is not monotonic. Take the sequences n square over 2 the power of n minus 1, which is neither increasing nor decreasing, are not monotonic. So the sequence can be classified into monotonic and non-monotonic. There are methods by which we can determine the monotonicity of the function. Among them, to determine the monotonicity of the sequences, there are the methods. The first method is consider the sequence an as a function fa. Consider the sequence an as a function f of n that is equals to a of n, which is defined on 1 to infinity, If a derivative of n is greater than 0 for all n, if a derivative of n is greater than 0 for all n, then an is increasing sequence. Then an is increasing sequence, and if a derivative of n is less than 0 for all n in the domain of this sequence, then an is decreasing sequence. So using the derivative is one way by which we can determine the monotonicity of the sequence, of the function. If an, that is a formula by which the sequence is defined, is continuous on an interval 1 comma infinity, consider that sequence as a function and then derivative. If that derivative is greater than 0 for all n, then that sequence is increasing sequence. But if the derivative of that formula is less than 0 for all n in the domain of the sequence is a decreasing sequence. There is also another method by which we can determine the monotonicity of the sequences, sequence, that is the second method by which we can determine the monotonicity of the function is using the difference between two consecutive terms of the sequence. That is, if an plus 1 minus an is greater than 0 for all n, then the sequence an is increasing sequence. The sequence an is increasing sequence, is increasing. But if an plus 1 minus an is less than 0, that implies an is greater than an plus 1. So the sequence is decreasing. Then the sequence n starts from 1. The sequence an is decreasing sequence, is decreasing sequence. So taking the difference between two consecutive terms and using the derivative is two methods by which we can determine the monotonicity of the function. There is also one additional method by which we can determine the monotonicity of the sequences that works only for a positive sequence. That is, for a positive sequence an, a positive sequence an, if an plus 1 over an is greater than 1, then the sequence an is increasing sequence. But if an plus 1 over an is less than 1, if the ratio between two consecutive terms of the sequence is less than 1, then the sequence an is decreasing sequence. So these three methods are a method by which we can determine the monotonicity of sequence. Let me give you an example. Determine the monotonicity of the following sequence. Now let us determine the monotonicity of those sequences. We can use one of these methods to determine the monotonicity of sequence. The ratio between two consecutive terms. Solution. Let us see the sequence given in A. That is, an is equals to 3n over 4n plus 1 implies an plus 1 is equal to 3 times n plus 1, that is 3n plus 3 over 4 times n plus 1 plus 1, that is 4n plus 5. Now, an plus 1 over an is equals to 3n plus 3 over 4n plus 5 over 3n over 4n plus 1, which is equal to 3n plus 3 times 4n plus 1 over 3n times 4n plus 5. 4n plus 5. That is equal to 3n times 4n is 1 to n square plus 3n plus 50n, that is equal to plus 15n plus 3 over this times this 12n square plus 50n. That is equal to 12n square plus 50n over 12n square plus 50n plus 3 over 12n square plus 50n. This one can be written in this way. Which is equal to 1 plus 3 over 12n square plus 15n. This one is positive for all n, for all n, an element of non-negative integer. So 1 plus this one is a number greater than 1. This one is greater than 1 for all n, an element of these sequences. Therefore, the sequence 3n over 4n plus 1 is increasing sequence, Let us see the second one, that is an is equal to 2n plus 3 factorial over n plus 1 factorial, which implies an plus 1 is equal to 2n plus 2, that is 2n plus 2 plus 3, 2n plus 5 factorial over n plus 1 plus 1, n plus 2 factorial, now an plus 1 over an is equals to 2n plus 5 factorial over n plus 2 factorial all over 2n plus 3 factorial over n plus 1 factorial. That's equal to 2n plus 5 factorial times n plus 1 factorial over 2n plus 3 factorial times n plus 2 factorial. So 1 is equal to 2n plus 5 times 2n plus 4 times 2n plus 3 factorial, 2n plus 3 factorial. 2n plus 5 factorial is equal to this one, times n plus 1 factorial is there, all over 2n plus 3 factorial, 2n plus 3 factorial is there, n plus 2 factorial is equal to n plus 2 times n plus 1 factorial. And this can be simplified as 2n plus 3 can be cancelled by 2n plus 3, n plus 1 factorial can be cancelled. So this ratio is equal to 2n plus 5 times 2n plus 2 is equal to 2 times n plus 2 times n plus 2 over there is n plus 2 here, which is equal to 2 times 2n plus 5, that is equal to 2 times 4n plus 10, 4n plus 10, that is greater than 1, that is greater than 1 for all n element of the domain of the sequences. Therefore, the sequence 2n plus 3 factorial over n plus 1 factorial is increasing. Next, let us see this sequence D, that in which an is equal to 5n minus 2 over 7 times n plus 3. If we consider this sequence as a function, this implies a derivative of n. A derivative of n is equal to the derivative of this one, that is 5 times 7n plus 3 minus the derivative of this one is 7 times 5n minus 2 all over 7n plus 3 the whole square, 7n plus 3 the whole square, which is equal to, this one is 5n, isn't it? 5 times 7n is 35n plus 50 minus 35n plus 40 all over 7n plus 3 the whole square. This one is equal to, this can be cancelled, 9 over 7n plus 3 the whole square, 7n plus 3 the whole square. 29 is positive, 7n plus 3 square is positive for all n. This one is greater than 0 for all n, Therefore, the sequence 5n minus 2 over 7n plus 3 when n starts from 1 to infinity, this one is increasing. This one is increasing sequence. Let's see E, that is n over 2 the power of n. Let us use the difference to determine the convergence of these sequences. If an is equals to n over 2 the power of n, then an plus 1 will be n plus 1 over 2 the power of n plus 1, n plus 1. Now, let us see an plus 1 minus an, that is equals to n plus 1 over 2 the power of n plus 1 minus n over 2 the power of n. This one is equal to n plus 1 over 2 times 2 the power of n minus n over 2 the power of n. Here 2 times 2 the power of n is common, so 2 times 2 the power of n divided by this one is 1 times n plus 1 is n plus 1 minus this divided by this 2 times n is 2n. This one is equals to n minus 2 times n minus n plus 1 all over 2 times 2 the power of n. That's equal to 1 minus n over 2 the power of n plus 1. This one is less than 0 for all n greater than 1. 1. Therefore, the sequence n over 2 the power of n is decreasing sequence. Sequence is a decreasing sequence. Therefore, this one is all about the monotonicity of the sequence and how to determine the monotonicity. Next, we will see the boundedness. So, bounded sequence, sequence. It is another way by which we can classify sequences that in turn used us to classify a sequence and then in turn used us to study the sequences. Bounded sequence. We say that the sequence an is bounded above 1, bounded above if there exists a number m such that an is less than m for all n. A number m such that an is less than m for all n in the domain of the sequence. And we say the sequence an is bounded below if there exists a number n such that m is less than an, m is less than an for all n. And we say that the sequence an is bounded if there exists m such that absolute value of an or the magnitude of an is less than m for all n. So we can classify the sequence by a boundedness. That is this one. A sequence n is bounded above if there exists a number m that is greater than all terms of the sequence. And if there is a number m that is less than all terms of the sequence an, we say that the sequence an is bounded below. And if there is a number m such that all terms of the sequence an is between minus of m and positive m, we say that a sequence an is bounded. A sequence an is bounded. If we take an example, a sequence an is equal to n, bounded above, bounded below. The sequence bounded below by 0, bounded below is bounded below. If you take an is equal to minus n, this sequence bounded above but not below, bounded above but not below. If you take the sequence n is equal to say 1 over n, say 3 plus minus 1 the power of n, take 2n over 1 plus n, are bounded, are example of bounded sequence, bounded both above and below. This one is all about the boundedness of the sequences. We say that the sequence is bounded if we can find a number m and all terms of the sequence is between minus of n and minus of m and m. The sequence an is said to be bounded sequence, And if you take n is equal to 1 over n, the first term of this sequence is 1, the second one is 1 over 2, and this sequence goes to 0 as n goes to infinity. So all terms of this sequence is between 1 and 0. So this sequence is bounded between 1 and 0. All term of this sequence is equal to 3 plus 1 if n is even, that is 4, and 2 if n is odd. So this sequence is bounded. This sequence is bounded. The terms of this sequence is 2 and 4. 2 and 4 that are bounded between 1 and 5, are between 1 and 5, or there. So this sequence is bounded. This sequence is bounded. This is also bounded sequence. There are the theorems that follow this definition of the sequence. That if a sequence is convergent, then it is bounded. If an is convergent, if a sequence an is convergent, that is the limit of an as n goes to infinity exists, then it is bounded. It is bounded, but the converse is false. But the converse is false. The converse is false, but the converse is false. That means if the sequence an is convergent, then it is bounded. That means its terms are between the first term and a number to which this sequence converges. A number to which this sequence converges. But boundedness does not imply the convergence. For example, if you take the sequences minus 1 the power of n, it is bounded but not convergent. If you take 3 plus minus 1 the power of n, is bounded but not convergent. Example of all sequences that are convergent are bounded. So example of a convergent sequence is an example of a bounded sequence. If a sequence an is unbounded, then it is divergent. If an is unbounded, then it is divergent. If unbounded, it is divergent. Divergent. There is a theorem that is monotonic convergent theorem, monotonic sequence theorem. Monotonic sequence theorem. Monotonic sequence theorem. every bounded monotonic sequence is convergent. This theorem states that every monotonic bounded sequence is convergent is convergent. So if the sequence is monotonic and bounded, then it is convergent. Let me give you an exercise. Show that the sequence defined by an is equals to, say, the square root of 2, and an plus 1 is equal to the square root of 2 plus an is convergent. Show this one. And next I will come with another tutorials. This enough. Okay, thank you, the listeners. It is enough for today. Next, I will come with another topic, that is the infinite series. Thank you so much.